Welcome to statistics. We're going to talk about probability. Now, you cannot have a good, solid discussion about statistics without having a solid understanding about probability. The entire root of statistics is probability. It's what are the behaviors that we're dealing with. And this is a fundamental aspect that a lot of people have with statistics that causes them problems. And this is very evident in our society. There's a huge chunk of our society that is probability, their probability literacy skills are subpar. And that is not to be mean, that's just an observation. And as a result, we don't necessarily understand probability. And as a result, we don't understand statistics the way we should. And I've even had mathematical colleagues when I taught high school who struggled with this idea as well. So it's something that we could all do better with. This is not an indictment. This is just simply an observation part of it. So there's my commentary. All right, so now what about probability? Probability is a ratio. It's the ratio between the wanted outcomes and the total outcomes that are possible. And one of the things people have, one of the issues people have with probabilities is separating this idea between the short-term and the long-term behaviors. Short-term behavior of any event is more or less unpredictable. That long-term behavior, though, is more based on a pattern that we can see, but we can't necessarily make predictions about the next outcome. So I have this example for us to look at here. So this is a problem I've used on a lot of different settings, and it has to do with flipping a coin 40 times. Now, if this is something I've stolen from someone else, but it's something I use with students a lot. And what I did, and you can pause this, read through the actual question, and do this yourself. I strongly encourage you to just kind of hit pause, read through that blurb right there, and then do as it says. Because the outcomes here are kind of interesting. And you can replace that word classmate with someone else who lives in your household, or a coworker, or whoever else you can find that might be interested in doing this activity with you. But what I did over here on the right-hand side of your screen was I actually went through and created 3 columns of fake flips and 1 column that is a real flip. And in this setting, I'm not going to tell you which one is the real and which is the fake, but one of those is fake. One of those is real and 3 of those are fake. And I asked people which one's the real and which one's the not. Now, if you're in my class, I'm actually going to create this as a discussion board and ask people to answer this, and I'll give my class the answer. But here in this setting, I'm not going to do that. I'm going to ask you to pause and look through these 3 columns of flips here. And this is 20 flips, this is 40 flips here. And I want you to try to identify which column represents the real flipping of the coin. And the numbers down at the bottom represent the number of times tails occurred in each of those flips there. The idea behind the probability, though, is the outcome. So flipping a coin, and this is something that is kind of interesting to deal with, is flipping a coin means that you can get heads or tails. Both events are equally likely. So when you flip a coin, you're always knowing that, I might get heads, I might get tails. You might be prone to go after B or C as being the correct answer. And when you look at that, you see that I picked those 2 because they are both roughly 50-50 in their outcomes. The question then becomes, do we have a big enough set here to really deal with that? Because remember, the idea behind short term, it's unpredictable. The long term is where we see the pattern. How far out do we really have to go to see that pattern? For coin flipping, you actually have to go out for quite a ways. You have to go up into the 4 digits before you really see the pattern truly emerge and stabilize according to the number of outcomes you get. So that you can use that as a little bit of an indicator of which of these 4 columns is actually the real one. And actually that doesn't help you at all. Like how do we identify that? Because the idea here that we're dealing with is this idea of randomness, which means that there's no predictable pattern in the behavior, meaning that we don't know what the next coin flip is going to be. So you say you picked D as the column. That's the column that was the real one. Well, what are you basing it on? What is the is that column really more likely than column C or column B or column A? You say, well, A only had 12 tails in that column. That's not close to 50-50, but that column that represents a very small collection of outcomes for us to look at. So we're dealing with a short-term look there. Are we really going to be seeing the pattern emerge in 40 flips? The number that we're actually dealing with here, the magic number, really is right around 2,000 when we start to see that pattern truly start to emerge and stabilize. So 40 flips really isn't enough for us to be able to see that. So the simple fact is, if you were to go through the idea of probability with all those different values, what you would find is that each of those columns is equally likely to occur. And some of you are thinking it's equally likely to get 12 tails out of 40 flips versus 22 tails out of 40 flips. Yes, it is. Those two events are equally likely because flipping the coin the first time, what's the probability of getting a tail? 1/2. What's the probability of getting a head? 1/2. You go through that, you iterate that out every single time. So what's the probability of getting 12 tails and 28 heads? Well, that is 1/2 to the 12th power and 1/2 to the 28th power, which simply means you're doing 1/2 to the 40th power. In all 4 instances, you're doing 1/2 to the 40th power, regardless of however many tails or heads you're predicting are going to occur. So each one of those columns actually has the exact same outcome. And that is actually how you do that. You multiply the probability of each individual event to get out to see how many you'd come, okay, or what the probability of the entire outcome would be, okay? So probability models, sample space, a lot of times we refer to that with an S, and that is the set of all possible outcomes of a random phenomenon. So when we say a random phenomenon is like rolling a dice or flipping a coin, those are random phenomenons because they are unpredictable in their nature. There's no way for us to know whether or not we are going to get a 6 or get a 1 on the next roll. There's no way to know whether tails is going to be what's going to occur next when we flip the coin, because of a big thing. All those events are independent of all the other flips or rolls of the coin. Those are independent, which means that the randomness of each individual one is maintained regardless of what has happened before or what happens after that particular event. Event's actually the next one that we're talking about is a particular outcome of a random set of outcomes. It's a subset of the sample space. Okay, so we said the sample space is a set of all possible outcomes for a random phenomenon. And so if we're talking about flipping a coin 40 times, that sample space is huge, because how many different ways can you flip a coin 40 times? How many different ways can you get heads and tails on 40 different flips? It's a lot of outcomes. It's a huge number of outcomes. And then you're essentially talking about 2 to the 40th power right there is the number of outcomes you'd have. And that is, again, legitimately how you'd figure that out. Just like if you're talking about rolling 2 dice, well, that is 6 outcomes on one dice, 6 outcomes on the other dice. That's 6 times 6, or 6 to the 2nd power, which is 36 outcomes. So if you're rolling 2 dice, there are 36 possible outcomes in the sample space. If you're talking about flipping a coin 40 times, you're talking about 2 to the 40th power possible outcomes for that. If you're flipping a coin once, there are 2 outcomes for that. So the sample space would be 2, and individual outcomes would just be would be tails or heads. Now, the probability model. So these are mathematical descriptions. And the idea is that we're seeing a random phenomenon occur, right? And we're creating a mathematical description to have some way to play around with or use or exploit what we're seeing occur inside that phenomenon. And that's what probability is. So all this is creating a rule and a system in order for us to better understand, describe, and work with that phenomenon that we're seeing. It's nothing mystical or anything like that. It's just some type of outcome that we can't predict, but we want to be able to apply some type of maneuvering to that. Now, if you think about this in terms of statistics, we find that we're doing a study with a particular new drug, and we give this drug to 100 people, and 90 people respond favorably to the drug, meaning whatever the ailment was eliminated by the drug. Well, that's 90 out of 100. That's your probability model. That's saying 90% or zero point 0.9 of the people that received this drug were cured or their symptoms improved as a result of this drug. So that means you have a 90% success rate. The probability of a positive outcome is 0.9. And that's what we're talking about. That's what that statistics gives us. It helps us explain this phenomenon so we can put some numerical values to it and be able to have a more in-depth discussion and be able to use the data and be able to use the outcomes here. So we have a couple different ones, probability models we can talk about. The uniform probability distribution. It simply means that all events are equally likely. It's kind of like rolling a dice or flipping a coin, a single die. So if you roll a die, it gives you a uniform probability distribution, meaning all events are equally likely. If you flip a coin, that means all events are equally likely to occur. Normal distribution is if you were to flip two coins, and that gives you something that looks like a bell curve, because there are occurrences that are more likely than others, and it is symmetrical. Rolling two dice and getting a sum of 7 is the most common, or the most likely single event. But symmetrically, getting a 6 or an 8 are equally likely, and going out in either direction from there. Those are normal distributions. Now the difference though is that we're talking about discrete versus continuous distributions, and we'll talk about that here in just a second. Probability, all probabilities lie between 0 and 1, meaning that you can have a probability of 0, you can have a probability of 1, you can have any value between 0 and 1. So all our probabilities are decimals between 0 and 1, including the endpoints there. Okay, 0 means whatever the event is impossible. It can't happen. So if you say the probability for this event is 0, not happening. If it's between 0 and 0.5, it's unlikely. 0.5, it is equally likely events to occur. 0.5 and 1 means it's more likely to occur. Actually, I guess I should have put less likely for 0 to 0.5. And then the probability equal to 1 means that the event is occurring. There's no doubt about it. It has to occur. Now, what we want to do is compare this back to the idea of randomness, though. So let's just say that an event has a probability of 0.9. What that means is it's highly likely or more likely to occur. But that doesn't necessarily mean if it's a random event, it doesn't mean that it is going to occur more often than not. We might actually, whatever this event is, that it has a probability of 0.9 occurring, we might actually be able to go through 90,000 trials and come up with it failing, right? Because the probability is 0.9. That doesn't mean that the actual outcome is going to occur 9 times out of 10 or 90 times out of 100. If we have a probability that's based on the statistical model, that is based on historical data. It's not giving us information about predictability going forward in terms of saying, oh, this is definitely going to happen with 90% of the population. The odds are good, like it's a more likely event, but it doesn't mean it's a definite thing. It just means that we're probably going to see more people respond favorably to this drug than not. It doesn't mean necessarily that it's the smoking gun, so to speak, type event. All right, probability rules. Again, all probabilities, P of A, whenever we write P with parentheses, we know we're talking about a probability. So in this case, I'm saying the probability is greater than or equal to 0 and less than or equal to 1 at all times. P of S. S is the sample space, so the probability of getting something that lies within the sample space is 1, meaning the sum of all the individual parts and pieces of the sample space have a sum of 1. Each individual piece of that has a probability of 1 when we add all the pieces together. If A and B are disjoint, now let's talk about disjoint for a second. Disjoint means that there is no overlap between the two events that we're talking about. So if we're rolling a dice or rolling 2 dice, we want to know the probability of rolling a 4 and getting a sum of 2. Meaning we roll the dice and either dice comes up as a 4, and rolling the dice and getting a sum of 2. Those events are disjoint. There's no overlap between those two events because we're never going to roll a 4 and get a sum of 2, nor are we ever going to be able to get a sum of 2 and have a 4 as one of the dice. You want a better example of that is if we say something is not disjoint, it means that we do have overlap. So maybe we were talking about rolling a sum of 6 or rolling a 4. Well, 4 and 2 occurs twice in that process, so that means that those two events are not disjoint. 4 is actually a subset in that instance. Well, it's not necessarily a subset. There is some overlap. If we were to draw Venn diagrams, there would be this intersection between those two locations. So there's not a disjoint because there's an overlap between that, because 4 can occur with a sum of 6. And if we roll a 4, there's a possibility that there's a 2 that we rolled, so we get 6. And if we roll a 6, there's a possibility of getting a 4 and 2, which means that we also have met the other requirement of A or B. So A and B can actually coexist, which means that there is overlap, which means that they're not disjoint. Disjoint just simply means there's no overlap between the possible outcomes. All right, rule 4, and these are our 4 big rules about probabilities here. The probability that something doesn't occur is equal to 1 minus the probability that it does occur. So this is kind of like a yes or no type event, or true false. Q is almost exclusively used for false. P is exclusively used for true. So what we're saying here is that P of false, the probability of false, is equal to 1 minus probability of true. Okay. When we talk about probability, we have a couple different models we can talk about, and I've already mentioned normal and uniform distributions. We also can talk about the idea between finite and continuous. So finite models, it simply means just that. There's a limited possible set of outcomes. For instance, rolling a dice is finite. If you're rolling one die, you have 6 possible outcomes. That's it. There are no other possibilities, and there's nothing also between rolling a 1 or rolling a 2. You can't roll a 1.5. I've never seen a dice kind of stand on its corner. I guess it's possible with some training. I don't know. But the idea is that these are discrete quantities. We can actually count them out, and there's separation between the possible events. Continuous probabilities, on the other hand, meaning what's the probability of getting 1.5 or 1.6 or 1.7? So in that case, it's not rolling a dice. It's doing some other type of thing. Now, assigning probabilities under the idea is that we could be able to draw a curve and find the area under that curve, and that is our density curve, if you will. That's the probability. That's a continuous part of that. Normal and uniform distributions are continuous. Now, this is the thing. Rolling dice can act like normal and uniform distributions, and sometimes we will treat them as that under the guise of them being actual discrete values as opposed to being continuous values. I have an example here we're going to work through, and this is actually a continuous example that we're going to look at, and it happens to be a normal curve. And the idea being is whatever the outcome, whatever this backstory is on this, is that we're saying that this is a normal curve with a mean of 64.3 and a standard deviation of 2.7. And I have the graph there so you can see what we're dealing with. Okay, so we're looking at the height in inches of individuals, whatever the backstory is along with this. I really didn't concern myself with that part. I just wanted you to just kind of see the mechanics of how this is really working, to see how these rules affect you to being able to find and work with these statistical models. It's the idea of the probability of an individual being between 68 inches tall and 70 inches tall, given a normal curve, and that's what the end of that first sentence means, the normal curve, where the mean is 64.3 and the standard deviation is 2.7. So we start off with the probability model, and we're going to switch this over to a z-score, or a standard normal, okay? And the idea is that we subtract the mean and we divide by the standard deviation, and we get our z-values. And those z-values correspond on our table. We get out our and that's another video I went through with y'all, is you get out your z-table and you actually figure out where those values lie on your z-table. Notice that when I switched right there, I switched it from being a inequality range, going from 1.37 to 2.11, z being in between, that when I switched that over, I actually switched it from being z is less than or equal to 2.11 minus z is less than 1.37. Now, we got to look over here at the graph. So the idea here is we're saying that first part of that, z being less than or equal to 2.117, that came from the individuals who are 70 inches tall. Meaning, what's the probability that someone is 70 inches tall or less? So we're figuring out that entire list. Now, we're not concerned with that in this problem, but that's where we have to start with this. So now that we know the probability that someone is 70 inches tall or less, 70 inches or less, that is 0.9826. So 98.26% of the population is, according to this, whether this is male or female, I forget which it is, this particular curve is 70 inches or less tall. And then we figure out the probability of someone being 68 inches tall, which in this instance was the z is less than or equal to 1.37, which was 0.9147, which is roughly 91% of the population. So now what we do is we subtract those two pieces, and we find that the difference between them is 0.0679, which means the probability that somebody is between 68 and 70 inches tall inclusively is 0.0679, or 6.8% of the population approximately. So if we were to pick, another way to look at this is if we were to pick somebody out at random out of a population, what we would find is that roughly 6.8% of the population would be meeting this mark. So how likely is it that if we were to select a person at random, that they would meet this between 68 and 70 inches tall? To give you reference, that'd be between 5'8" and 5'10". So what is the probability that the people fall under that realm there? Fairly low, right? So we're talking about a fairly small group of people here. If we were just to walk in off and grab somebody and say, well, what's the probability that person is in that realm? They are 68 or 69 or 70 inches tall. Keeping in mind that this is a continuous curve, which means we could even talk about there being 68.2 or 68.3 or 68.4, all right? So that's the idea behind how we would use these ideas behind probability to determine these statistical models or information about these statistical models, all right? And the last piece of that, and what we were working with there, was a random variable. And that random variable is just the numerical outcome that we are concerned with. So there's some type of random phenomenon, and we want to know more about it, and we can use these probability distributions and incidentally the random variable to allow us to be able to talk about or find the values that can be with that. And these values, these random variable values, can be finite or continuous. So in the one we looked at, yes, people are finite in the terms that there's only a limited number of people, and there's a heights are fairly standardized, so you're not necessarily talking about a continuous look of heights there. But the population, when we start getting to really huge values, we can start to treat those populations or those samples as being continuous, and we can use these probability models with them. Now, it changes a little bit when we're dealing with a finite model, and I'll try to create some videos that go along with the idea of how we work with this with finite models as well. I hope these are useful. Please reach out with questions, comments, or the request for additional videos. Take care.